Okay, I guess we're on the air. First of all, are there any questions that dealing with either correlation analysis or regression analysis? Before we move on to talk about experimental validity. No? Let me then overview experimental validity, because it doesn't follow naturally in the progression of topics. We have spent some time now talking about various data analytic techniques, all the way from z-tests and t-tests, which are about as primitive as you can imagine in terms of analyzing data, through to more sophisticated techniques such as analysis of variance and regression. What I want to do now is to examine some of the threats to experiments. Some of those threats are threats to essentially the internal structure of the study. And some of those threats are essentially threats to the external nature of the study. In fact, this discussion used to be divided into discussion of, on the one hand, internal validity, and on the other, external validity. And you don't have to write any of this down, because there aren't going to be questions on the exam about this. I'm just trying to overview it so it makes sense to you. Internal validity has since been broken down into two separate units: internal validity and statistical conclusion validity. External validity has been decomposed into external validity and construct validity. Regardless of those changes, we're still essentially talking about things that are either internal to the experiment, to the study, or external to it. And what we're going to look at is a series of threats that can mislead or affect the generalizability, mislead the researcher, or affect the generalizability of the study. Okay. Are there any questions about experimental validity in general? First of all, then, let's look at threats to internal validity. Internal validity. And the first that I'm going to take a look at is something that we've discussed in another context, and that's measurement unreliability. Measurement unreliability. We observed previously, when we were talking about measurement reliability, that true scores do not equal observed scores. You and I are forced to treat observed scores as if they are equal to true scores. That is, we look at our watch and it says 10, 15, and 23 seconds or whatever it is, and we treat that as real. We are driving along in our automobile and we look down at the speedometer and it says 73 miles an hour, and we treat that as real. We take our temperature and it says 101.7, and we treat that as real. What you and I should have understood by this point is that none of those scores are likely to be real, because we distinguish between true scores and observed scores. True scores are equal to observed scores plus or minus some amount of error. And then in the context of measurement reliability, what you and I spent time doing was decomposing and examining this error component. We distinguished between systematic error and random error, and talked about systematic error affecting validity, measurement validity, and random error affecting measurement reliability, and that's how we progressed. But if we can distinguish between true scores and observed scores, we can also distinguish between observed correlations and true correlations. That is, it seems to me not, and in this instance, RxX simply means that we're correlating a variable at time 1 with itself at time 2. This is test-retest reliability. It seems to me a comparatively small leap from the notion that observed scores do not equal true scores to argue that observed correlations do not equal true correlations. Yeah, it seems to me intuitively apparent that that should be the case. If you're dealing with observed scores that are not equal to the true scores, then when you correlate those observed scores, what the correlation is going to involve is not simply the true correlation, but some amount of error. Because the observed scores that you're dealing with include some amount of error. So we can distinguish between observed correlations and true correlations. And in fact, the observed correlation, and let me go back a moment here. Let me cast this in terms of bivariate correlation, so that we're dealing with the correlation between X and Y. And having made that correction, let me talk a little more about the difference between observed and true scores. If the observed X scores involve error and the observed Y scores involve error, then it seems to me intuitively reasonable that when you correlate those two sets of scores, each involving error, that the resulting correlation is not equal to the true correlation. Would you agree? Because the X scores that you've used involve error, and the Y scores that you've used involve error. In fact, the relationship between observed and true correlations is that the observed correlation equals the true correlation multiplied by the square root of the reliability of the instrument you use to measure X, multiplied by the square root of the reliability of the instrument you used to measure Y. And we can reconfigure this equation such that Rxy divided by the square root of the test-retest reliability of the instrument used to measure X multiplied by the square root of the test-retest reliability of the instrument used to measure Y equals the true correlation. Would you agree? Yes? Let's take an example then. Let's assume that the observed correlation between X and Y is 0.3. If you recall, if R equals 0.3, R squared equals 0.09. Yes? Which means that only 9% of all of the variance in the X and Y scores is shared. Which might be seen as a relatively weak relationship. Would you agree? Yeah? That is, this is a situation with an observed correlation of 0.3 in which the researcher might fail to reject the null hypothesis. Because the observed correlation is a relatively weak one. If we, however, knew the reliability of the instrument used to measure X and the reliability of the instrument used to measure Y, we could compute the true correlation. Let's assume that the reliability of the instrument used to measure X is 0.8 and that to measure measure Y is 0.7. That is, we have two adequately, this is 0.8 and this is 0.7. Yeah? I just saw you squinting. I thought it was my writing. I always attribute these problems to myself, you know. That is, we're dealing with two instruments that are adequately reliable, that we would conclude are reliable. If we perform this, if we plug and chug this computation, we would find that the true correlation, in fact, is not 0.3, but 0.4. That is, the amount of shared variance between X and Y is not 9% as we estimated on the true observed correlation, but in fact 16%. Would you agree, first of all, that given this evidence, rather than this evidence, it is now more likely that the researcher will reject the null hypothesis? Because the correlation between X and Y has increased. It has become stronger. So there is now a greater likelihood that the researcher will reject the null hypothesis. Yes? Would you agree then that if one depends on the observed correlation, there is an increased likelihood that a researcher will fail to reject the null hypothesis? Yeah? Pardon?
Say that again.
Say that again? Oh, you don't. That wasn't. Let me go through this all again. Let me start at some other point. Most generally, because of measurement unreliability, would you agree that the observed correlation underestimates the true correlation?
Yes.
It might be useful if you all paid attention here. Not for me, but for you. But who knows? Perhaps I'm just interfering with your understanding. Because of measurement unreliability, the observed correlation underestimates the true correlation. And this will always be the case to the extent that both instruments are not perfectly reliable. If both instruments were perfectly reliable, would you agree that the true correlation would be 0.3 divided by the square root of 0.1 multiplied by the square root of 0.1? of 1.0 rather. 0.3 divided by the square root of 1.0 multiplied by the square root of 1.0. This would indicate, 1.0 would indicate that the instrument being used was perfectly reliable. So even when you're dealing with perfectly reliable instruments, which you never are and no researcher ever is, the best case scenario is that the observed correlation will equal the true correlation. To the extent that one or both instruments are less than perfectly reliable, then the observed correlation will always underestimate the true correlation. And the more unreliable the instruments become, the wider that gap will become. If we took a second example here, with an observed correlation of 0.3 and two instruments, each with a reliability of 0.6, would you agree that this is now 0.3 divided by the square root of 0.6 multiplied by the square root of 0.6, which is 0.6, and 0.3 divided by 0.6 is 0.5? That is, as these instruments have become even less reliable, the distance between the observed correlation and the true correlation has grown. If we compare scenario 1, in which the instruments were comparatively reliable, with scenario 2, working with the same observed correlation, the discrepancy now in scenario 2 between the observed and the true correlation is greater than it was in scenario 1. And that is the case because these instruments have become less reliable. First of all then, to the extent that one or both instruments is not perfectly reliable, the observed correlation will always underestimate the true correlation. Second, as those instruments become increasingly unreliable, so the discrepancy, the underestimation of the true correlation will increase, as we've seen here. Third, because researchers normally have to rely on observed correlations, to the extent that one or both instruments is less than perfectly reliable, there is an increased likelihood that the researcher will fail to reject the null hypothesis. All you have to do is imagine two researchers, one who is working with fallible data, an observed correlation of 0.3, and the other researcher who's working with infallible data and knows that the true correlation is 0.5. The researcher who has to rely upon the observed correlation, which is normally the case with researchers, is more likely, would you agree, to fail to reject the null hypothesis? If you fail to reject the null hypothesis, what is the only kind of error you can make? A type 1 or a type 2 error? If you fail to reject the null hypothesis, the only type of error you can make is a type 2 error, a beta error. So that the bottom line of this is that measurement unreliability increases the likelihood of a researcher committing a type 2 or beta error. Measurement unreliability increases the likelihood that a researcher will make a type 2 or beta error, because it increases the likelihood that the researcher will fail to reject the null hypothesis. Observed correlations underestimate true correlations. That is, to the extent that one or both instruments is not perfectly reliable. Second, as measurement unreliability increases, that discrepancy, that underestimation increases. So that measurement unreliability increases the likelihood that a researcher will fail to reject the null hypothesis, which means that measurement unreliability increases the likelihood that a researcher will commit a type 2 or beta error. Are there any questions about measurement unreliability? No? There are other threats to internal validity. And let's take a look at some of those. Let me say parenthetically something for my own protection. Measurement unreliability is discussed now as a threat to statistical conclusion validity. Don't worry about that. Because there's not going to be a question on the exam that asks you to associate a threat with a type of validity. What I'm trying to do here is simplify the discussion so that we're looking at things that are essentially internal to the study versus things that are essentially external to the study. Before going any further, let me distinguish between two types of experimentation. There is true experimentation and quasi experimentation. True experimentation and quasi experimentation. True experimentation typically takes place in some sort of contrived environment. And that environment is one over which a researcher has complete or near complete control. The true experimentation is a sort of lab study. So that a researcher can control what enters that environment and what doesn't enter that environment. The researcher can control what enters the environment for one participant and what enters the environment for another participant. And we looked at examples of this when we were working through data analytic techniques. A researcher can control, for example, how much violent television content a participant watches. A researcher can control the amount of medication that a participant in a medical study receives. So true experimentation is essentially laboratory research, and that allows a researcher to control either completely or near completely what enters that environment and what doesn't enter that environment. Quasi-experimentation occurs in naturalistic environments. Quasi-experimentation occurs in naturalistic environments. That is, you actually go out and look at the thing where it occurs. If you're interested in the effects of violent TV on children's subsequent behavior, and you're doing this naturalistically using quasi-experimental methods, one approach would be to go into the homes of some number of children, unobtrusively videotape or observe in some way the amount of violent TV they watched, and then unobtrusively videotape or somehow record their subsequent behavior. You understand, in that sort of environment, it's very rich in its realness. See, surely one of the criticisms of true experimentation is, yeah, but people don't really act like that unless they're in a laboratory. Well, no wonder. If we go back to the issue of the effect of violent television content, when you show TV content to children, it's not unusual to have a proctor in there who directs the child's attention to the TV monitor. That is, when the child's attention starts to wander, somebody brings it back to the TV content. That's surely unreal. And that's the sort of primary criticism with true experimentation, that you're often forcing people to behave in ways that contrast with how they behave normally. And you're also simplifying the environment, manipulating the environment. Well, if we look at quasi-experimentation, see, it seems to me that in quasi-experimentation, these experimental settings are rich in their reality. Some child sitting at home watching TV. His or her attention wanders, they get up, they get some food, they're interrupted by parents, they're interrupted by siblings, they're interrupted by noise in the house, whatever it is, the dog jumps up on their lap. All of that happens in real life. But you understand it all gets in the way of the pathway between the stimulus and the participant. So in general, true experimentation controls well for threats to internal validity because the researcher can control that internal environment. Its weakness is in terms of external issues. Quasi-experimentation has exactly the opposite pattern of strengths and weaknesses. Its weaknesses are in terms of internal issues because researchers can't control the dog jumping up on the kid's lap. It's rich in external sorts of issues because it occurs in naturalistic environments. Having said that, pardon? The strengths and weaknesses? You mean I've got to say this again? I tell you, in somebody like me, saying anything twice. Of course I can. True experimentation is characterized by a high degree of control over the research environment by the researcher. Would you agree? So that its strengths have to do with these issues of internal validity. Because the researcher can control what is internal to the experiment, to the study, can control the environment, can manipulate the environment. But the argument generally is that what the researcher is doing is creating what is in many respects an artificial, an unreal environment. So that the question then is, can you generalize from what somebody does in a laboratory, research laboratory at the University of Houston, to what they do in their own home when the researcher is absent. That is, the strengths of true experimentation have to do with internal sorts of issues. The weakness of true experimentation have to do with external sorts of issues. Quasi experimentation occurs in naturally occurring environments. Somebody interested in the effects of violent television on children's behavior and who was employing a quasi experimental design would go into the home of the child or of the children participating in the study and would unobtrusively observe those children and their television watching and chronicle the amount of violent content they were watching and so forth. The strength of that, it seems to me, is its naturalness. That is, its strength has to do with external sorts of issues. Its weakness has to do with its ability to control threats to internal validity. Because, as I've said, the researcher can't stop all of the noise that gets in the way of, that enters into that pathway between the stimulus and the participant. The researcher can't prevent the dog jumping up on the kid's lap. Can't prevent siblings running in and wanting to play. The researcher cannot prevent the lapses in the child's concentration or attention to the TV. Cannot prevent the child from changing the channel. So the weakness of quasi-experimentation has to do with with issues internal to the study. Is that, yeah? Oh, you're what? No. You're welcome. I do think, by the way, just as an aside, it occurs to me, I think having witnessed the birth of my own child and been very close to the birth of my grandchild, I think I'm now probably equipped to deliver children myself. You just need a good drugs person, you know? There was pandemonium going on in there, I tell you. The next threat then that I want to talk about is a threat of history. Thread of history. Let us presume, hypothetically, that you're interested in the effects of a breathalyzer test on the number of traffic fatalities. So you go to a particular location and you spend some time, or you can rely on archival data to generate observation 1. That is, you measure the number of fatalities that occur at this location across some period of time. The treatment X, the breathalyzer, is then introduced. And now you go back and measure a second time over an equivalent period of time the number of traffic fatalities that occur subsequent to the introduction of the breathalyzer test. Let us assume that there were 102 fatalities during the first period of measurement and 75 fatalities during the second period of measurement, and that this treatment is a breathalyzer test. Would you agree that what you want to do, what the researcher wants to do now, is attribute this reduction in traffic fatalities to the treatment? That is, the researcher wants to argue that the number of traffic fatalities has declined because of the breathalyzer, introduction of the breathalyzer test. Yes? An example of a problem of history would be if the speed limit had also been reduced during the time that the breathalyzer was introduced. That is, threats to history occur when some co-occurring event can explain the observed outcomes without having to appeal to the treatment. And we could explain the reduction in traffic fatalities without even invoking the breathalyzer test, yes? Because we would expect that traffic fatalities would decrease if the speed limit were reduced. What you have here is a co-occurring event that explains the observed outcomes all by itself, so that you do not have to invoke the treatment, in this case, the breathalyzer test. You understand that in naturally occurring environments, this is quite likely to occur because you have multiple stimuli being introduced into the environment almost simultaneously. If you have, they've done, here we are. If you have a temporary reduction in speed limit, you have road work in this area during during at least part of the measurement period, you would expect this sort of outcome. Because when people drive slower, they're less likely to have an accident in which one or more people die. Are there any questions about this issue of history, threats due to history? Another problem, another threat to internal validity is maturation. Maturation is a problem when a discrete change occurs in the sample or population. When a discrete change occurs in the sample or in the population. Here's an example of a discrete change occurring in a sample. If you're interested in reading ability in 5th graders, you go in at time 1, you measure the reading ability of these 5th graders. The average reading ability on some test of reading ability is 20. You introduce some treatment, some new text, or some new teaching method that is purported to improve 5th graders' reading ability more than anything else can. So you introduce this treatment. You then go back at the end of the semester, you administer a similar or the same test of reading ability to the same group again, and you compute the average score, and the average score is 25. So the average reading ability of the group has gone up from 20 to 25. Would you agree that you as the researcher want to attribute that improvement to the new teaching method? Yeah? That's the whole purpose of this scenario. The problem is, of course, that if you leave fifth graders alone, if you don't do anything to them, their reading ability will improve over a semester. Because that's just the nature of maturation. Again, you can explain the observed outcome without having to appeal to the treatment. Because in this instance, a discrete change has occurred in the sample. They've eaten their vegetables, they've eaten their proteins, they've got their vitamin supplements, and they've matured. Maturation effects have occurred. The cells have started to come together. The neurons have started to fire. Here's an example of a discrete change occurring in the population. If we go back to the first example dealing with the breathalyzer, if between observation 1 and observation 2, the proportion of drivers under the age of 25 decreases, that is, now it's not the sample, the population, as has happened in the United States, simply gets older. If there are proportionally fewer drivers under the age of 25, can that explain a reduction in traffic fatalities all by itself? If you believe the insurance companies, it can. That's why you folks pay probably less insurance than I pay, but then they've learned that I'm really 7 driving a car. But that's why, on average, you folks pay more insurance, automobile insurance, than I. In fact, you folks ought to have your own roads. You know, go out and have wrecks amongst yourselves. Just stay away from me. You also ought to have your own parking lots. You know?
Amen. We do.
Yeah, you ought to have your, yeah, that's right. That's why we have the gated ones. And I will pay for that gated parking lot, believe me. You know? You drive around with your mid-European import. You don't care what you hit. You know? Bang. Oh, bang. It's my car. If there is a discrete change in the population such that there are now proportionally fewer drivers under the age of 25 at time 2 as opposed to time 1, one would expect that the number of traffic accidents would decrease, and so the number of traffic accidents involving fatalities would decrease. Here, a discrete change has occurred in the population, and what is more, you can use that change to explain the observed outcomes without having to appeal to the treatment, the breathalyzer test. Are there any questions about maturation effects? No? I got a list of about 20 or 30 of these. I can just run through them endlessly. Let's take a look at testing. Testing is a problem when persons become either generally or specifically familiar with the nature of the test. And you know this. You know this. Because you will do, several of you have invoked a couple of strategies. You come to me before the first exam and you say, how many questions are there going to be on the exam? What kind of questions will there be? Can we have a look at previous exams? In fact, could we have a look at the exam we're going to have next Tuesday? surely the whole logic in the questions that you ask, and they're reasonable questions, is that if you know how many questions there are, if you know the type of questions, if you see a previous exam, you are likely to do better on the real exam than you otherwise would have done. That's a benefit to you. I mean, the ultimate effect of familiarity, example of familiarity, is where you break into my office, steal a copy of the test, or you photocopy, do something spyish, like, you know, and you've got the actual test, and you're familiar with the actual test. This is a benefit to you. It's a problem in research. Again, if we go back to the reading example, we could explain the observed outcomes simply as a function of testing. That is, the students who took the test at time 1 became either specifically or generally familiar with the test, and so did better at time 2. And this has been argued by several people in the class. After exam 1, several people said to me, "Now I know what your exams are like, you little fiend, and I will do better now on exam 2 because I know that." That's an advantage to you. It's a problem in research. When participants become even generally familiar with the nature of the test, the likelihood is that their performance at time 2 or time 3 will improve. That is, their performance across trials will improve. Yeah. Problems due to testing. Let me look at one more, and then the problem of mortality. The problem of mortality. When mortality occurs, you typically think in a study, you typically interpret that as people dropping out of the study, yes? People dropping out of the study is not a problem. People dropping out of the study is not a problem. And this happens, for example, in long-term research, that is sort of repeated measures research, such as medical research. It happens all the time. If you're asked to go you report to your doctor says you've got high cholesterol, then you get a note from Baylor College of Medicine saying we're doing a test on a new medication to treat high cholesterol, would you please be a participant? You go down there, you're locked in for 24 weeks of whatever it is. After 6 weeks, you just stop going. You fall out of the study. You're an example of mortality in the study. And people dropping out of the study is not a problem. It's when different sorts of people drop out of different groups in the study. Mortality, perhaps I ought to say that again. Mortality is a problem when different sorts of people drop out of different groups. If you have a weight loss program and you randomly assign participants to either a control group or to a treatment group, who are the people least likely to, or who are the people most likely to drop out of the treatment group? The relatively heavy people in the treatment group or the relatively light people? People who don't, the less you weigh, the more likely you are, it seems to me, to drop out of the treatment group, because the less benefit is coming to you. Who's more likely to drop out of the control group? I would say it's likely to be the people who weigh a lot. You've got different sorts of people dropping out of different groups. And if you now think about what that does to the average weight of the group, on the one hand, when the heavier people drop out of the treatment group, the average weight of the group goes down. When the least heavy people drop out of the treatment group, the average weight of the group goes up. So you can actually have a significant treatment effect. That is, the weight loss program can work, but it can be masked by mortality, because different people have dropped out of different groups. Mortality is a problem in research, not when people fall out of the study. It's when different sorts of people drop out of different groups. Okay? Are there any questions about anything? Okay. Don't move. I'm finished, but you ain't. I have before me the dreaded course evaluation. And what comes along, what comes along with this is, I'm like a magician here. I need a volunteer from the audience.